So basically what we're going to be looking at here in this section are functions which repeat themselves over periods of values, periods of x values, and for looking at stretching or shrinking or moving graphs around the coordinate plane. For example, if I look at the graph y equals f of x given above here, and I were to then multiply each output, each f of x by 2, instead of being here at this point, I'll have jumped up to 2. Instead of being here at 1, 0, oh, that y value won't change because 2 times 0 is still 0. And instead of having a maximum or minimum value down here of -1, if I multiply that output by 2, then I'm going to be down to -2. So we'll look at some translations, horizontal and vertical first, which we looked at before this year. Big idea here is if I replace x in a function with x minus 2, that will move my graph 2 units to the right. And a simple example from a quadratic, comparing x squared to x minus 2 squared. The point 0, 0 gets moved over 2 units to the point 2, 0. Note, if I put in 2, 2 minus 2 is 0, and at 2 I'll get the same thing as I got at 0 over on this graph. So for an x value and input of 0, I got 0 out. If I put 2 in here, I'm going to get the same output as if I had put a 0 in on the original graph, and that's going to occur when x is 2. So that point, my vertex has moved over 2 units to the right. Replace x with an x minus 2, I move 2 units to the right. So if replacing x with x minus 2 move 2 units to the right, if I replace x with x plus 3, I would guess that I'm going to move 3 units to the left. And indeed, comparing absolute value of x with the absolute value of x plus 3, I move my v 3 units to the left. Note, putting in a value of -3 here leads me to what I had when I put a 0 in over here. So putting in a 0 gets me a 0. Putting in a -3 here is going to get me the same output, or 0. I've moved my v 3 units to the left. So if I replace f of x with f of x minus 2, that's going to move a graph 2 units up. For example, if I look at the absolute value, or so if I look at the square root of x, and I then look at this h of x minus 2, replacing h of x with h of x minus 2 equals the absolute value of x, that's going to move my graph up 2 units. Note that I could do some arithmetic here, move the 2 over to the other side, and that might allow you to see better that h of x equals root x plus 2. Take each output, and you're going to be adding 2 to it. That's going to move it up 2 units. And indeed, that's what we've done. And clearly, if I replace r of x with r of x plus 7, that's going to move my graph down 7 units. So comparing x cubed to r of x plus 7 equals x cubed, which is equivalent to r of x equals x cubed minus 7. That will simply take each point and move it down 7 units. So instead of looking at replacing x with x plus 2, or y with y minus 7, f of x minus 7, suppose I were to multiply each output by a number. Clearly, if I multiply each output by 3, each output will be multiplied by 3. If I multiply f of x by a quarter, each output will be multiplied by a quarter. Note, this multiplication here isn't going to change the zeros as we saw in the first page here of this presentation, because if I have an output of 0, 3 times 0 is still going to be 0, or a quarter times 0 will still be 0. Now I say the tough ones here for some transformations of graphs are these two, where I replace an x with a multiple of x, and that multiple could be something along the lines of 2x, where my absolute value of my multiple is bigger than 1, or the absolute value of my multiple is between 0 and 1. And it's a little counterintuitive what happens here, kind of the same thing as it was if we replaced x with x minus 7, we moved to the right 7 units. And you would think if you multiply by 2 that might stretch things out, or if you multiply by a half, that might shrink things. So let's take a look and see what happens. So let's consider f of x equals x squared compared to f of x equals 2x quantity squared. I've replaced the x with 2x. And I've plotted some points for these graphs. I've kept the y-axis the same for each one. Note what happens for my inputs here for these y outputs. Inputs of 1, 2, 3 yield me 1 and 4 and 9 as my outputs. To get an output here of 1, to get an output of 1 here, for example, I need to put something in here for x so that this 2x will give me a 1 because 1 squared is 1. I'd have to put a half in. If I put a half in, 2 times a half is a 1, and 1 squared is 1, so 1/2 is going to correspond to 1. Same thing to get an output of 4 here. I need this input to be a 2. What would make that input a 2? X is 1. Look at your scale here. I've gone from 1, 2, 3 to 1/2, 1, 3/2. We call this a horizontal shrink by a factor of 1/2. So replacing x with 2x results in a horizontal shrink by a factor of 1/2. So again, if I replace x with a quarter x, my intuition might be, well, this is going to be some sort of stretch. Well, do the same thing we did before with the previous. Here I've got a graph of absolute value of x, and I want to keep the y values, my y coordinates here, arranged the same, and ask myself, if I want to get an output of 1 here, what would I have to put in for x to get me an output of 1? This whole thing would have to be 1. What makes that 1? 4. If I want to get an output of 2, what would I have to put in here to get an output of 2? I'd have to let x be 8. Notice your scale here for the x-axis, 1 to 2 to 3 over this y-scale. My scale here now is 4, 8 to 12 over this y-scale. What have I done to change this graph to this graph? Is I've horizontally stretched my graph by a factor of 4. Now, I will add in here that you can view what we just did with some horizontal stretches and shrinks with the functions that we're looking at for now. We could view them also a little differently. I can view replacing x with 2x in this quadratic, as I did, as a horizontal shrink by a factor 1/2, but I also could do some simple algebraic simplification here and find out that 2x quantity squared is 4x squared. That's a 4 times f of x, which will actually be a vertical stretch by a factor of 4. So in this case, for my quadratic x squared, replacing x with 2x is, I could say, it's equivalently either a horizontal shrink by a factor of 1/2 or a vertical stretch by a factor of 4. Now, what's going to be really important as we head on to trigonometry and some trig functions is the idea of a function that's periodic. And certainly periodic is something that repeats regularly. Your text is going to mention things like tide, like light during the day, over a period of days. You have things that repeat over time periods and repeat quite regularly. So one way to view a periodic function visually is to say, look, if you can take a function and slide it a certain number of units left or right, and if you see the same picture again, in other words, if it lies on top of itself by sliding either right or left, then you've got a periodic function. For example, what we've drawn here, if I were to slide everything over 1 unit to the right, I'd see the same thing. If I were to slide everything over 2 units to the right, I would see the same thing. And again, I'm assuming that this function continues. Its domain is all reals, and this function continues its pattern on and on. I could slide this whole thing over 6 units to the right or 12 units to the left. I'd see the same thing. So what we're going to want to talk about is what the fundamental period of a function is, and it's the smallest such fixed amount that I could slide left or right and see the same thing. In this case, my fundamental period would be 1. The amplitude of a function is simply the amplitude of a periodic function, because we were going to talk about amplitude only for periodic functions, simply going to be a max value minus a min value divided by 2. So if I'm looking at this periodic function here, and I'm assuming again it repeats, I've got a maximum, I've got peaks at 5 and valleys here, low points at -5. So my max minus my min is going to be 10 over 2 or 5. Another way to look at that, to find amplitude, is to find kind of your midway axis between the between your max and min, and look at half of that. So I can see that this is 5 and this is 5, and that's my amplitude of 5. Now, there are some other changes, modifications, in addition to these stretching and shrinking things that we've looked at so far. If we change a function, for example, looking at f of x gets changed to negative f of x, or f of x gets changed to an absolute value of f of x, etc. These changes here are going to involve some sort of line reflection, and they're outlined for you on page 142 in a lovely colored box. And we'll look at a couple of examples here, and then you're going to want to make sure you understand the others. So considering my function here, f of x equals root x, if I were to look instead at f of x equals root of negative x, I've replaced x with negative x. And you can again say that's a multiplicative factor in here of -1. So I'm replacing x with -1 times x. What is that graph going to look like? Well, the square root of x is going to be half of a sideways opening parabola. My domain's x is greater than 0. My range is f of x is greater than or equal to 0. How about for square root of negative x? Well, what can my domain values be? If I've got a negative here, if I put in 2 or 3 or any positive number, I'm going to get an imaginary number here, which we know can't happen if we're graphing on the real coordinate plane. So my domain here is I've got to put in only numbers less than or equal to 0. And if I do that and plot some points, I'm going to wind up seeing that my graph of the square root of negative x is simply a reflection of the square root of x over the y-axis. So let's take a look at what happens if I were to replace f of x equals x squared minus 4 and take the absolute value of f of x. So then f of x equals the absolute value of x squared minus 4. If I think about it, any output that I've had before, if it's a positive value, does the absolute value change it? And the answer is no. So I know from my original graph where I'm positive, there are no changes. What's going to happen for negative values? Well, whatever negative value I have, I'm going to take its opposite positive value. So for example, if I had an output of -1 over here, it's now going to become an output of 1. If I had an output over here of -4, my output over here now is going to become 4. And that simply is going to take and reflect all negative values up over the x-axis. Because if I've got a -2 down here, that's going to correspond to a +2 up here if I take an absolute value. Note that there's not going to be any change here for those positive y values. So while I do get a reflection, if I replace f of x with the absolute value of f of x, the reflection only involves places where the original graph has negative output values. So I'm only reflecting where my original values of the function are negative. The positive values remain unchanged because the absolute value of a positive number doesn't change anything. You're still going to get that same positive number.